Last time we finished the final discussion on the combustion characteristic for the diffusion frame. And as you remember, I tried to mention there is some missing regions between the two category premise frames, pure premise frame and a pure diffusion frame. There's a mixing region between them, and we need to learn some combustion characteristics from this region. That means if you go back to the stability limit for the from the the premix regime to the diffusion regime, there is the region, and this region including the those kinds of combustion catalysis spatial stabilization for the diffusion, for the jet diffusion frame. You can see there is some change depends on the concentration, oxygen concentration you have inside of the jet flow. Now you try to think about, can we change the frame structure by changing the boundary condition? In the beginning, we try to make a definition for the premise frame and the diffusion frame. For the premise frame, we simply say that the oxygen will premix with fuel in the upstream side, and they will support the propagation premise frames. But for diffusion frame, fuel and oxygen are separated by the diffusion frame itself, which means the definition on boundary condition for premise frame and the diffusion frame are quite clear, and they are completely different. But think about, if you use the so-called opposed jet flow, from our experience, you will figure out that when you have opposed jet flows, simply if you try to control the mixing ratio in the upper flow and the lower flow are the same. For example, you look at the figure for case A here. They tell you if you control, for example, this is there is you look at this figure 8, and here this is a temperature profile, and there is some concentration profile for oxygen and fuel. Now we try to evaluate the combustion characteristic from this plot. You can imagine, actually, the left-hand side, you can think about the flow coming from the lower burner, and the right-hand side represents the flow coming from the upper burner. And for both cases, you can see this plot as has shown you the symmetric curves. And for the right-hand side and the left-hand side, they show you oxygen concentration is higher than the fuel concentration, which means you will have a so-called the dim premise frame in the right-hand side, right? Because in the right-hand side, oxygen has a higher concentration than that for fuel. And here they are premixed together. Then you expect you will have a so-called premise frame. Actually, you can specify this as the dim premise frame. Okay, here LPF represents dim premise frame, or you can call premise frame in this case simply because both of them are premix. Okay, and they are identical. When you have two identical frames, you can expect ideally they will burn to the same flame temperature. Therefore, in the downstreams, they will remain a constant temperature profile. Okay, this is a typical plot for a double flame generate in the opposite jet flow. You can have this kinds of flame structure. Later on, I will use the experimental observations to give you the more insight to understand the flame structures. And here, since they are both of premise frame are dim, then they should have some oxygen depth in the downstream side without any fuel depth in the downstream side. The downstream side means for these two premise frame will exist in the center region, and you can expect the stagnation plane will just sit in the middle. This is a case A for you to understand. Now you have a two dim premise frame exist in your opposite jet flow. Now think about can we change the concentration differently? Okay, you can see from look at the case B. If you look at, we need to identify the mixing ratio for both friends. You can see for both of them, actually oxygen and the fuel will mix together in the upstream side, right? And you can say most of the premise friend actually is a premise. Most of the friend are premise friend, and the oxygen and the fuel will be burned completely at the flame position. That means that these two frames basically they are stoichiometric, okay, and they will reach to highest temperature point at the flame locations. Okay, for these two frames, you can see there is the flame temperature in the right hand side, and there is a flame temperature in the left hand side. But they tell you the flame temperature of the premise flame in right side is higher than the other one, which means the temperature profile will have a gradient. Show you the temperature in the right hand side is higher than that in the left hand side. Now, how to interpret those kinds of situations? In this case, they tell you these two frames, both of are under stoichiometric conditions, but in a posture flow, you can premix a certain amount of nitrogen, right? Then those nitrogen will absorb the heat. Then you will see there is two stoichiometric frames, but they show you different flame temperature, and those flame temperature may be influenced by the heat absorption from the nitrogen. You can expect in the left-hand side, the amount of nitrogen is higher than that in the right-hand side. Since you have more nitrogen in the left-hand side, then they will have some heat release to the nitrogens, absorbed by the nitrogen, then the temperature becomes smaller. Okay, in this case, what happened, you need to think about. For the premise flame in right hand side, actually heat is as a higher flame temperature, but for the left hand side, the premise flame actually usually you find out if you consider the adiabatic case, for example, the case A, the downstream temperature, if you have two identical premise flame, actually the temperature will remain constant in uniform temperature in downstream, and these kinds of variation, these kinds of temperature variation referred to so-called adiabatic case. But for the right-hand side, the case B, the right-hand side, the premise flame actually they experience heat loss from the flame position to the downstream side, and the lost heat will be used to support the burning of the premise flame in the hand side. Then you can think about for the premise flame in the left hand side, we can say this flame is or was superheating. Okay, superheating means they can additional heat coming from the downstream to support their burning. But for the premise flame in the right hand side, actually they just play a very normal role because they just tell you they have some heat release and the heat loss to the premise flame in the left hand side. Okay, for the case B, they just tell you simply there is some heat transfer between these two flames, and those heat transfer can be identified by the temperature gradient, which means they were governed by the thermal diffusion. Okay, this is a simple thermal impact for these two non-identical premise flame. Even both of them are stoichiometric, but the flame temperature are not the same. Okay, and they were influenced by the inert in the left hand side or in the right hand side. You need to think about that. Okay, this is the first one you need to think. Now we go to the case C. Now the interesting thing is at first we need to identify what kinds of flame we have. Okay, for the left hand side, oxygen higher than the nitrogen, higher than the fuel. Then you have a dim premise flame in the left hand side, and also you have a dim premise flame in the right hand side. Okay, both of them are dim premise flame. But when you look at the concentration profile, okay, especially you can see because the dim, all the fuel will be burned completely. Therefore, you do not have a fuel left in the downstreams. Okay, in the region between these two frames. But you can see there is the different amount of oxygen supply from both sides, and actually there is the extra oxygen depth in the downstream side. Also, you have an extra oxygen depth in the downstream side, but you can see the results of the unburnt oxygen in the downstream are different for both frame. Actually, the excess oxygen in the premise frame in the left hand side is higher than that in the frame in the right hand side, which means you can see there is the so-called oxygen concentration gradient, right? Now, when you see this kinds of oxygen concentration gradient means you will have oxygen diffuse from the left-hand side to the right-hand side, right? Now, when you think about the diffusion, the oxygen diffusion from the downstream side to the premix frame, actually this is not the normal definition for premix frame, right? Because for our premix frame, we understand all the diffusion of fuel and oxygen were coming from the upstream side. Now, for the premise frame in the right hand side, you already have oxygen and a fuel diffusion from the upstream to the frame. This is a very clearly you can observe it, but you can see there is additional oxygen diffused from the downstream side. Okay, this is the not fit with our definition on premise frame. Then for this premise frame, actually we add a P in front of the PF in abbreviations. We say this is so-called the partially premise frame. The partially premise frame means this is not a purely premise frame. In previous two cases, case A and case B, basically they show the purely premise frame, even they are under Dean conditions or stoichiometric condition, but all the boundary conditions will obey the definition of the premise frame. You can see oxygen and fuel supply from the upstream side and diminish it in the downstream side without any gradient occurs in the downstream side. Okay. Now for the diffusion frame in case A and the case B, actually those boundary conditions fit very well with the original boundary conditions for the premise frame. But for case C, they have some modification because you have oxygen diffused from the downstream side to the premise frame positions. Then we include this kinds of effect to premix burning. Then we call this is a so-called the partial premix frames. Okay, the burning structure mainly is controlled by premix frame, but they have an additional influence coming from the oxygen diffusion from the downstream side. Okay. And here you can see they still have a temperature gradient exists, and this is normal. You just expect there is some heat loss to the surrounding or heat loss to the premise frame in the left-hand side. Okay, this is additional conditions you need to consider to think about. They may have some additional oxygen diffused from the left-hand side from downstream to the premise frame. By the same token, you can think about they may have a fuel coming from the left-hand side to from the downstream to diffuse to the fuel. Okay. Now the thing is you will go to the case D. Now case D, we try to bring two different kinds of premise frame. One is the lean, the other is rich from the upper floor and the lower floor, and then mitigate what's happened. You can see in the right-hand side, this is a rich premise frame because the fuel concentration is higher than oxygen concentration. Then you will have some excess fuel left in the downstream sides, okay, for rich premise frame. And for lean premise frame in the left-hand side, originally oxygen concentration higher than fuel concentrations, and you will have excess oxygen left in the downstream side of the lean premise frame in the left-hand side. Okay, and for both premise frame, actually they are normal. Okay, because they show you the supply of fuel and oxygen from the upstream sides. Okay, but the interesting thing is in the downstream side, what happened From the right-hand side, you will have some excess fuel left in the downstream, right? And then you have oxygen concentration left in the downstream side of the dim premise frame. Those oxygen and the fuel coming from both sides, and they will meet in a certain position in the region between dim premise frame and the rich premise frame, and you will find out oxygen coming from the other side, fuel coming from the one oxygen coming from one side, fuel coming from the other side. They meet together. They are separate, right? And meet together, which means they may produce a so-called diffusion flame. Okay, here this broken line tell you there is a possibility to have a diffusion flame exist here. Okay, and in this region, originally, if you go back to the case A, if they have the same burning intensity, temperature will remain constant. But in this case, since you have additional burning by diffusion flame, you may reach to a higher because you have an extra heat release. Then you will bring the temperature become higher at certain point. And in the middle, maybe in the middle of this the region between LPF and RPF, they will have a highest temperature here. Then you can figure out here for dim premise frame, for rich premise frame, actually they are superheating by the diffusion flame in the middle. Okay. Okay, this is a very interesting structure. They tell you, in this case, you have a so-called triple flame. I will use the experimental result to justify this kinds of consideration. It is very interesting to tell you, if you try to bring different kinds of flame together, and you try to change those kinds of boundary conditions, you have a different kinds of flame characteristics cannot be well described by originally pure diffusion flame or purely premise flame. Okay, but we still need to consider another cases. Now you look at the cases as E. Yeah, I need to mention here this part actually already include in your lecture notes. I think it's a page 1.47. Okay, because I use the PowerPoint, it's easier to explain it rather than using the slides. But later on, we will go back to see the slides because there is some parts we need to use to give you some explanation. Now we go forward to look at the frame structures for the case E. Now they still have a two frame, right? Now we try to look at the conditions for the frame. You need to identify at first. You look at the frame in the right hand side. Fuel concentration is higher than oxygen concentration. Then you identify this as a rich premise frame. We use the RPF, rich premise frame. Okay. And the right-hand side, you supply oxygen with fuel, but fuel is a very small amount, okay? Which means that this flame is very thin, and maybe this should not be exist, right? Because when the fuel is too thin and the concentration is lower than the mixing ratio is lower than the thin limit, then you may not have a premise flame, okay? But here you can see they still can support an additional flame here. Now we try to justify what kinds of flame it is. Okay. In the right hand side, you will have a fuel left, right? And this fuel is you have a large amount of fuel. If this fuel is large enough, can be mixed with oxygen coming from the hand side. Actually, they can burn here. But now you try to think about what kinds of flame you have. You have a fuel coming from both sides, right? And oxygen coming from only one side. Now the question is it premise flame or diffusion flame? Depend on the importance of boundary condition will influence of your burning. When you look at here, the fuel coming from the right hand side has a higher concentration than that from the left hand side, right? Which means the burning of this flame is governed by the fuel diffused from the right hand side. Okay, Now, the major fuel for the burning from the right-hand side is separate by the diffusion flame with oxygen from the left-hand side. Then you figure out fuel coming from the one side, oxygen coming from the other side. Then we say the nature of this flame surely mainly controlled by diffusion. Then this is a diffusion flame. Now, this is the first one. You need to identify the nature, the major nature of this burning. Now, this is a diffusion flame, but the condition is not completely perfect to be defined based on the boundary condition for diffusion flame because you have additional fuel coming from the left-hand side, which means this small amount of fuel has already a premixing with oxygen. The premixedness is a small influence on this flame. The dominant burning structure basically controlled by diffusion. Then we say this is a so-called the partially diffusion flame. The similar way to think about the name, for example, I tell you the so-called partially premixed flame means the major burning is controlled by premixed burning, okay, but modified by diffusion. Then they say it's a partially. But for the partially diffusion flame, they tell you this flame majorly controlled by diffusion of flame structures, okay, and modified by certain amount of premixing, maybe in the oxidizer side or maybe in the fuel side. You can reverse it, and you can make a good definition on this on the nature of this flame. Now look at the final cases. They tell you have both of the fuel and the oxygen support from both sides. Okay, but you need to identify a little bit here in the right hand side. Oxygen just a small amount, but fuel concentration in the left hand side is also small amount. Therefore, you can see the major reactant to support the flame, the burning in the middle, basically fuel in the right hand side, oxygen in the left hand side. They are separate. Then you can say this flame should be controlled by the diffusion burning. Then you will have a diffusion flame, but you may have some influence from the premixing of fuel in the left hand side and the premixing of oxygen in the right hand side. Then we modify the name. We say this is so-called the partially diffusion flame. Now you can see by changing those kinds of boundary conditions, the flame structure may give you so many opportunities, and they tell you by these kinds of situations, you may have different temperature distributions, and the oxygen or fuel may depth in the downstream site. You think about a turbulent combustion model, you see there is so many AD, right? And one of the AD maybe just have a fuel itself, and the other one maybe have an oxygen itself, and these two AD meet together. Supposedly, you will find out they have a diffusion flame because fuel and oxygen AD are separate, right? But in many cases, you may have a pre-mixtures inside of your AD, for example, dim mixtures, and the other is rich mixtures, or maybe just the pure fuel mixtures, and you all possibility you may have. Just like you change those kinds of boundary conditions from the upper burner and the lower burner, you can generate different kinds of flame structures you may have. Okay, this is the first idea to tell you. Originally, the definition for premixed flame and diffusion flame basically is pretty much ideally or theoretically. Even you can show it from the experimental results, but they just tell you those kinds of fundamental burning characteristics. Now you go to the realistic burning structures. You need to try to change your mind to think about those kinds of boundary conditions can be changed. Your nature of premixed flame and diffusion flame will be modified by those kinds of additional, maybe small amount of boundary condition change, but they still give you some effect. Okay, for example, there is a so-called superheating, right? The high temperature to the low temperature show you the temperature gradient, then you have thermal diffusion. Now, if you think about the oxygen still continue diffuse, for example, here diffuse from the flame to the the other friend, then there is another diffusion process. Okay, for example, in the case E, the fuel coming from the right hand side will support the diffusion friend and burner with the oxygen together to generate the diffusion friend. Okay, those kinds of excess fuel or excess oxygen, sometimes they can modify your frame structures based on from the downstream from different sides of your frame. Now let's look at the experiment results. This actually this experiment, I did this experiment and in 30 years ago, when I was in Northwestern University, I tried to bring those kinds of ideas as I described in previous slides to justify it by experiments. Okay, and we did this experiment by using the opposed jet flows, and we try to control the fuel mixing coming from the loader frame, loader burner, and the oxygen coming from the upper burner. And we hope we can fix the stagnation plan almost the same without too much change. Then we mix certain amount of nitrogen from the upper flow and the lower flow, and they can balance it without have too much variations on the position of stagnation plan. Okay, now by do the so-called conservation systems, because overall the total volume flow rate for both of the lower burner and the upper burner will keep the same, and the total volume flow rate for the nitrogen, methane, and oxygen are also keep the same, which means we just shift the fuel from the lower burner to the upper burner. Fuel oxygen shift from the upper burner to the lower burner. That's it. We just change the boundary condition without changing the total amount of the fuel and the oxygen available for burning. Okay, then we call this is a so-called conserved system, which means you just simply think about, I just supplied the same amount of methane, the same amount of oxygen, the same amount of nitrogen. Okay, this is a fix, and I give you try to produce a different kinds of flame in these kinds of opposite structures. Okay, this is a very interesting experiment. We're starting from the case one, or this is step one. This is a very nice diffusion flame. Okay, diffusion means there is a concentration different. There is a mixing ratio definition. Omega, U represent the upper burner, L represent the lower burner. Okay, and omega simply is a ratio between the fuel and the oxygen ratio. Okay, fuel divided by oxygen, the boiling ratio. Okay, and you can see here for the first step, omega U equal to 0, which means their upper burner, there is no fuel. Okay, and for the lower burner, they go to the infinity because in the lower burner we just have oxygen only. Okay, fuel is there is some fuel, but oxygen is 0. That means a certain amount of value divided by the 0, then will go to infinity. Okay, the first case, this omega U and omega L 0 and infinity represents fuel coming from the lower burner and oxygen coming from the upper burner as initial conditions. Okay. Now we tried to bring certain amount of fuel from the lower burner to the upper burner. Okay, when you have a small amount of fuel add in to the upper burner, then you can see fuel oxygen ratio increased to 1.68, right? Okay, that continuous go bring the fuel to the upper flow. You can see the omega U continuous increase, right? So you can see 5.42, and here I think this is a make a mistake. I did not. How come this is a 3.48, 5.9? This is your continuous increase. I think this is a make a mistake. Oh, I did not see clearly here, and the paper is already published. I am sorry about this. Maybe yeah, this is just a reverse. Okay, Actually, this is 7.5. Okay, 9.74, continuous, 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 up to here, 50. What's the meaning of 50? 50 means the fuel divided by oxygen is just equal to 50%. What's the meaning with 50%? Methane burning with oxygen as a stoichiometry is 1 to 2, right? 1 to 2 is a 50%. Okay, so by this kinds of change, the fuel, you bring certain amount of fuel to the upper flow, moving continuous. When you go back to the older fuel, go to the not an older fuel. When you try to control the concentrations ratios to the 50s, now in the upper flow, there is stoichiometric conditions. Okay, by this kinds of variation at the same time, when I add the fuel, we change the fuel to the upper burner. At the same time, we bring certain amount of oxygen from the upper burner to the lower burner. Then the omega L, they start to have a certain fuel, right? In the denominator, if you have a certain fuel continuously, then the overall omega L will be reduced, continuously reduced. Finally, they will reach to the 50-50, okay? Which means in this experiment, we control the ratio between the methane and the oxygen as they just as, for example, here you can see 92, and this is double of 92, right? 184. They already have a stoichiometric ratio in between the supply of methane and the oxygen. Okay, this is the boundary condition change I tried to describe. Simply say that initially you have a diffusion flame, fuel coming from the lower burner, oxygen coming from the upper burner, and mix well with the additional nitrogen, try to balance try to fix the stagnation plane as at the same positions. Okay, now experiment starts from diffusion flame. We bring certain fuel to the upper floor, and oxygen coming from the upper burner to the lower burner. By this kind of switching, step by step, and finally you will reach to balance 50-50% methane exists in both burners, upper and the lower burner. Then finally you can see there is the two symmetric identical stoichiometric flame, premise flame exist here. Okay, this is a purely diffusion flame. This is a purely two identical premise flame. But in the transition of these kinds of stepwise variation, you can see step by step, actually, by this kinds of shifting, the nature of diffusion flame still remain. Okay, flames sit very nicely, almost no change their position. But you can see maybe in the step 10s, you can see there is the blood region occur, right? There is a very light, very light color is actually they occur earlier, maybe step 9 and step 10. And at step 11, you can see there is a small flame appear, right? And this is a so-called dim premise flame that start to be built. Okay, originally it's a diffusion fuel coming from the lower burner, oxygen coming from the upper burner. Fuel site basically is controlled by the lower burner. Okay, and when you increase the oxygen in the lower burner, then generated the nature of the diffusion flame in the lower burner site, they will start to have so-called rich premise flame structures. But the upper flame, they start to have a so-called the dim premise flame natures occurs. Then when they strong enough, they start to have a so-called, because premise flame has the propagation speed, right? Then when you have a propagation speed, they mean speed, then they try to find a position to stabilize and meet with the flow supply velocity, right? Because they need to balance. Then you can see this flame is generates dim premise flame, and then they start to find a position to sit, because at that position, the flame speed can be balanced with the supply velocity from the upper burner. Okay, you can see the generations of the dim premise flame become stronger and stronger. Finally, at the last step, they separate. Okay, now by this kinds of stepwise variation on concentration distributions, you start from the diffusion flame, by changing the boundary condition to generate a double two identical stoichiometric premise frame. In this experiment, we do the measurement for the temperature distributions along the center axis. You can see this is show you very interesting temperature distributions. Here you can see the original, the step one. Here, this is the for the step one. This is the typical diffusion, the temperature profile for diffusion flame, right? The maximum temperature exists at this point. Is actually is a small one. Okay. Now you change the stepwise, step 6, 11, 12, 13, 14, 15, up to 16. Then the temperature profile actually they are changed. The temperature, a high temperature region extended. Okay, you can see up to the 11th. Okay, maybe a bit before 6. Actually, the temperature distribution is do not change too much. The high temperature zone become bolder, and the flame temperature increased. But later on, you can see a blue flame, the visible luminous zone appear around step. I think this is step 6. Step 6. You cannot see very clearly from the picture, but you can see from the experimental observations. But they do not change too much. But a certain time, a certain step, this step will belong to 12. Okay, or 11, this must be 11, then jump to the 12. Okay, 11 is still very closer to the original diffusion flame, but for the step 12, the flame separates. Okay, the flame separate, and then go to the 13, 14, and then they finally jump to the certain position very very abruptly. Here you can see this is step 15 here, right? And this means the limb premise flame as its identity to have its independent flame speed. Then they need to find locations to stabilize here. Okay. And but for the premise flame, actually they do not change. They follow the diffusion flames until there is some position here they separate. Okay, they separate. Then the diffusion flame date becomes a broad regions without a very strong intense burning for the diffusion flame identity. Okay, that becomes a broad. Okay, but you can see overall the temperature is continuing increase, and at the final step, actually they change to the rich premise flame, right? When I'm sorry, change it to the two identical stoichiometric flame. They jump to the broken line here. Okay, this is a broken line. Okay, by this kind of temperature profile, you can see when you change your boundary conditions stepwise from step 1 to 16, you can see the temperature profile. Actually, the region extended continuously. Surprisingly, you can see if you look at the overall heat release based on the temperature distribution, you can see all the temperature distributions give you a larger high temperature, which means you release a lot amount of heat compared with initial conditions, because this temperature profile is narrow. Okay. And when you go back to stoichiometry, then still you do not have a largest high temperature region. Now this one, this tell you when you have a certain amount of fuel and oxygen, you may try to think about, can I burn it as a diffusion burning or burning as a premise burning? And in this experiment, tell you for both a purely premise flame burning or a purely a diffusion flame burning, do not give you the maximum high temperature region, but you can find there is the maximum high temperature regions as you have a so-called the multi-flame structures. You have a limb premise flame, you have a rich premise flame, and in between you have additional diffusion burning. Then they will provide a broadened broaden high temperature region and give you the highest heat release rate. Okay, even you can see the flame temperature is increased continuously, right? And to the certain positions, and this highest temperature actually exists in at the step 15 or 14. Okay, and you can see in terms of the highest temperature, this is not cannot be identified from the purely premise flame or purely diffusion flame. For the multi-flame structure, you may have the largest high temperature region and the largest flame temperature, or we call this the highest temperature in this high temperature region, which means by using the multi-flame structures, you may have an optimal heat release and from the combustion process.